Okay, so hello everyone. Welcome to this session and welcome to my talk. Today I'm going to talk about the effect-oblivious equivalence. And this is joint work with my advisor, Stephanie Warwick. And so today's talk, I will be talking about three parts. First, what are effect-oblivious equivalence? And second, why effect-oblivious equivalence is useful. And at last, I will talk about how to actually define effect-oblivious equivalence. So as a first start, let me try to talk informally, intuitively, what an effect-oblivious equivalence mean. So we are talking about verifying a programming language. It can be any programming language. But to actually verify that, we want to use a theorem prover like a calc to verify for example, the semantics of a language of a program is equivalent to another program. So our optimization or transformation during compilation is correct. And to do that, the first step we need to do is to have a semantic model of the programming language. And the typical step for doing that is to have a semantic embedding in calc. And that is the focus of our work. We are focused on the semantic embedding step for programming languages. And we are talking about the equivalence in reasoning about programming languages under a semantic embedding in calc. So let's start with a motivating example. So I'm showing two programs here. The first one is add to 1, which just read an integer from two pointers, P1 and P2, and then add them together. The second one is almost the same, except it switches the order of the read. It's first read from P2 and then read from P1. Other than that, they are the same. And what is this read integer at? Well, it's an effect. It's an effect that reads from external environment. And the thing is, we do not know anything about the external environment. And so we have no assumption on that. So now the question is, are these two programs equivalent? Well, since this is a technical talk, and so apparently this is going to be a trick question, and the answer is that it depends. So, but it depends on what? So let's first consider something. Let's first consider, I've been talking about this read int at some pointer effect, that it is something that we don't know. Since we don't know, maybe we should discuss about what assumption we have about it. If we are reading, every time we read from, for example, P1 or P2, they are the same, and nothing changes. This is just a normal immutable read that we are expecting, and we are reading from an immutable word that never changes. These two programs are equivalent. But if this assumption are not true, for example, if the integers at P1 and P2 change over time, then maybe if we first read it from P1 or we first read from P2, this gonna matter because maybe during my next read, the values at these pointers would change. Another example is that the integers at P1, for example, if I read from P1, then the value at P2 would change. Or if I read from P2, the value at P1 would change. This is not so common in a read effect, but it would be much more common if we have some other kind of effect. So under these two examples, these two programs should not be equivalent. But let's back, but is that really true? It turns out that whether these two programs are equivalent also depend on something else. So in our previous setting, we say that those two examples are not equivalent because we have a default assumption over the program. We have a default assumption that these effects will be run and executed in a sequential order. But what if they are not? So for example, what if the two reads at P1 and P2 will happen in parallel? So in actual run, they could be in either of the program, I could be reading from P1 first or P2 first. So the order is non-deterministic, and the two programs would actually simulate each other. And the second example is that the two reads at P1 and P2 may be non-deterministically ordered. Well, it could be due to they are running in parallel, but it could also be run, for example, we are having a relaxed memory model or some other situations. And in this case, these two programs are actually equivalent. And they are equivalent with, even though we know nothing about the effects to read the integer at. So they are equivalent, even like the two examples, the two situations about read the integer at effects would happen. So when we talk about that, so whether the two programs they are equivalent or not, it depends, and it depends on two things simultaneously. Not simultaneously, sorry. It depends on two things. First, it depends on effects. That is something people have realized, but what we are not that is less well known is that there's also something that matters. That is the effect, what I call effect context. So let's get back to our topic today, which is about effect-oblivious equivalence. And the effect-oblivious equivalence is trying to reasoning about effect context and try to make effects abstract and reasoning about the rest of the things that would determine whether two programs are equivalent. So let me try to distinguish a little bit about what are effects and what is effect context. So some people would argue that parallel execution, etc., these are also kind of effects. But I want to try to make a final distinction here. So effects in my talk would be referring to new operations that has something to do with the world, like IO, exceptions, states, mutex. On the other hand, the effect context is about something that is more general. It doesn't add some new operation, but it has something to do with the entire program, and it has something to do with all the effects, how the effects are connected, and how the effects are executed. So this includes like a general mechanism for implementing language runtime. It includes control flow and data flow properties. So as we mentioned before, parallel execution would be a kind of effect context, and another effect context is like relaxed memory model. So we define effect-oblivious equivalence as follows. Two programs are effect-oblivious equivalent if the two programs are semantically equivalent, no matter how the effects are implemented. So we are kind of like treating the effects as abstract. We make no assumptions about the effects. We know nothing about how they are implemented. And under this notion, so we look at the two programs on the left. These are the two programs I showed initially in the motivated example. These two programs are equivalent under certain effect context. However, the two programs on the right-hand side, they are not effect-oblivious equivalent, because especially the add-to-2 program, we have a ret effect here. So we are talking about we know nothing about how effects are implemented, but we will try to distinguish different effects. So that's one important thing about the effect-oblivious equivalence, that we are treating them abstractly, but we are not totally ignoring them. So before I move on to, so these are all very informal. And before I move on to show how I define effect-oblivious equivalence more formally, I want to just talk briefly about why effect-oblivious equivalence would be useful. So there would be basically three kind of situations that is useful. the first situation is that the environment, the external environment is unknown. That we could be reading from anything, and when our compiler wants to do optimization, we should not be assuming anything. The second possibility is with algebraic effects. For example, our compiler is compiling some program with algebraic effects, and then later maybe there's another linker that links with a program with abstract effects with concrete effect implementation or effect handlers. And for the abstract effects, we will need to reason about effects abstractly. And the last part is that in a program that we will eventually know how the effects are implemented, it's still useful to have certain abstraction or refinement layers where we don't assume anything about effects. And so you can have some refinement layers that have less assumptions. And by having less assumptions, this is the proof would be more robust to changes. So for example, if we decide later that we want some different kind of way to implement our effects, or we have different assumptions, and we need to redo many proofs, but some of the refinement layers and some of the refinement proofs would still be kept with this kind of abstraction. So these are some examples why I want to care about this kind of equivalence. But how do we define effect-oblivious equivalence actually? The key here is I just want to bring the figure I've shown earlier. We want to the first step for verifying a program is we need to do a semantic embedding of the original programming language into something like a calc. And the key here is how do we do this embedding? And how do we do this embedding in a way that we can distinguish effect and effect context? So the common ways of doing semantic embedding, there are many different ways. And there's a spectrum of different styles of embeddings. On one side of the spectrum is deep embeddings, where we treat many all the syntax abstractly and up to interpretation. And another, on the other side of the spectrum is shallow embeddings, where we treat, we just translate a program, for example, we translate a program to just the terms in calc. And in my talk, I'm going to take a mixed embedding approach that treats some parts shallowly and some parts deeply to achieve effect-oblivious effect. So first of all, because I will be caring about effect and effect context, so I don't want to reason much about pure computation, so they will be treated in a shallow embedding. But for effects, I want them to be in a deep embedding. And so they will be in deep embedding and they will be uninterpreted so that we can achieve oblivious effects. And at last, we will also model effect context in a deep embedding way. But we will pre-equip this deep embedding deep syntactic structure with some semantic theory as well. So although it's deep, there's some way to reason about the semantics behind the effect context. So how do I embed this effect context deeply using deep embeddings? Well, it turns out that this effect context here corresponds to some of the familiar concepts we commonly find in programming languages like Haskell. And that is the classes of functors. So basically, how do we embed effect context? We use the classes of functors like applicative functors, monads, and selective functors, etc. Let me be more concrete by giving one example. So this is an example that basically effective context can be implemented by reifying a class of functor, which I will call the reification of a class of functor program adverb, because it takes it's basically describe how the effects are connected together. So if we treat so the analogy is that if we consider effects as verbs in a language, then effect context is like the adverb in the language. So in this slide on the upper side, I'm showing you the definition of applicative functor. I'm showing you in calc. It has two operations: a pure operation that lift a pure computation into something within the applicative functor, and lift a2 that connects two applicative functor together and returns something else. And we have a program adverb that reifying this applicative functor. And it's very clear to see that first we have a pure constructor, which just replace the functor f with the starting adverb data type here. And the same happens for diff a2. So I'm just copying the functions and replace the type with something more concrete. And in addition, I'm adding an embed data constructor, which would embed an effect into this adverb, which I call starting adverb. And as this name suggests, this adverb reified from applicative functor is called startingly because it describes a static dependency in a programming language. Just before I elaborate why it's a static dependency, some of you who's familiar with classes of functors or free structures might recognize that this is very similar to free applicative functors. It is indeed very similar, but it's not a free applicative functor because free applicative functors are normal forms of reifying applicative functor. As a contrast, I'm not converting the reification into a normal form. And the reason is that I want to keep more about the syntactic structure here. So let me show you that's why I call this adverb startingly. This is the key here is in the lift a2 operation. So lift a2 operation, we want to get something of fc, and the only maybe I can see my cursor here. So you will, if you want to get fc, the only way you can get that is by via the function from A to B to C and two inputs fa and fb. And so this dependency is this data dependency is fixed, and neither fa nor fb depend on each other. So this is a quite static dependency. This is especially in contrast with monads, which have the dynamic dependency. And what's the benefit of modeling static dependency? I will get that very soon. But before that, I have talking about the syntactic structure of reifying effect context. I need to talk about how to now that I can talk about how to define effect-oblivious equivalence. And defining effect-oblivious equivalence is basically that basically surprisingly the loss of the classes of functors. So taking a starting adverb as example, it has the congruence rule, it has the applicative functor loss, and there's also the equivalence properties, including reflexivity, symmetry, and transitivity. But that is not all of it. If we only have that, we are just modeling about normal static computation. What's the benefit of that? One benefit is that because we are modeling about static syntactic structure, we can now do static analysis over it. In contrast, if we are using a monad to model the semantics, we can now do static analysis. But more, for static dependency, we can now talk about the kind of effect context I mentioned earlier in the motivated example. The parallel execution or the non-deterministic execution order. And that is crystallized by this law here. This is called the commutativity law of applicative functor. And basically, if I run my arguments A and B, which have no dependency with each other, and I know that I must depend on these two operations, then if I flip the order of their execution, it's going to be equivalent. And when you use this law, we need to be careful though, because commutative applicative functors is not something, this role, unlike the roles I show here, is not a role that is satisfied by every applicative functor. So you can certainly imagine some applicative functor this law does not hold. However, what you can prove is that we can implement an applicative transformer, which is basically a power set applicative functor transformer that shows that no matter what applicative functor I originally have, I can transform that applicative functor to make the new applicative functor satisfy this law. So that is again a crystallization of what happens with our effect context I've shown earlier. But due to the time constraint, I cannot show the detail here. I'm happy to talk about the detail of that offline. And just for completeness, let me get back to the example and show how we can model effect-oblivious equivalence using the program adverse I show here. So first of all, we want to model the read effect. And we will model it in this way using this gathered here. And we do not have any interpretation of that. So that's how we treat it as an oblivious effect. And then the program add to one can be represented using this, basically it can be embedded in using this program. And the add to two can be represented using this program with some simplification, of course. And then we can show that these two programs would be effect-oblivious equivalent by applying the commutativity rule we have just shown earlier. And of course, we should only apply this rule when we know that we are modeling a semantics that has this property, such as parallel execution or a non-deterministic execution order. But now that we directly have this role in our embedding. So that's it. That's my talk today. But since this is a workshop, and I would like to hear from you, and I would like to discuss with many of you about the potential use case and limitations of program adverbs. For example, I'm very interested in learning more from you about do you have in mind like some other instances of effect-oblivious equivalence, some other instances of effect context? And have some other applications of effect-oblivious equivalence in mind? And or if you have any thoughts in general about effect-oblivious equivalence or program adverbs. And that's all for my talk. Thank you very much. Now I'm taking questions.
Thanks, Yao.
Thank you.
All right, and we are ready to take questions. Any question from the room?
Right. So does your effect-oblivious equivalence say, can it express network refinement?
That's an excellent question. So I've actually tried the program editors on network servers. And so basically, this is one example where I think that effect-oblivious equivalence can help with multiple abstraction layers. But first, the short answer is that it doesn't formally represent model network refinement yet. I don't know if it can. I haven't done that. But what I have shown is that basically for the entire network refinement, so I assume you are talking about the network servers in CPP 2019 that we work on. And so what I can show is that from the basically some part of the low-level C program and to some intermediate level of implementation model, their equivalence is captured by some sort of effect-oblivious equivalence. Although, okay, I'm probably talking too much here, but going too much detail here, but I also have a theory of effect-oblivious refinement, which I use to model the refinement to implementation model. But the actual refinement from implementation model to a higher level spec that considers network reordering, I have not done that.
Cool. Thank you so much. In the interest of staying on time, we'll move to the next talk. Thanks, Yao, again.
Thank you.